going to do some calculus here, derivatives of functions given in graph and table form, and some of the skills we want to possess about that. My name is McGrath. You might know me as MM. So given this graph, this is a graph of a derivative. This is f prime of x. Then we want to sketch these two. Okay, so sketching the second derivative, that's just sketching the derivative of this. I think, and so do most of the students that I've ever had, that that is easier than going backwards from f prime to f. So I'm going to do the easy thing first. All right, so let's see. Tried to get the right scaling on there. This is f prime, so what's, but I want to sketch f double prime, so that's just the slopes of these. So right here, the first thing I'm going to look for is, where's the slope 0? There's a maximum, so right here at 1, 2, 3, it looks like 1, 2, 3, I have a slope of 0. And on my way getting closer to these, I have positive slopes, but they're going towards 0. So I have positive slopes going towards 0. So somewhere up here going that way. And then after this, I have slopes that are becoming more negative, so headed down this way. You might say, oh, I should just make that a straight line. And you'd be smart to do that because a couple of reasons. I mean, unless you are very convinced that it's not straight, then, why would you guess at some kind of curvy shape to it? You also might be thinking to yourself, gee whiz, this looks awfully like some kind of parabola type thing, some kind of x squared. And, the power rule, so what's the derivative of an x squared going to be? It's going to be an x to the first, so it's going to give me some kind of straight line. And in fact, I did make this little graph here with some kind of quadratic. So this is the graph of f double prime. All right. How do we get back from f prime back to the original function? That's a little trickier because now we're looking at this graph and thinking, okay, these are the slopes. So these are like the numeric slopes. So here, I think what we want to do first is look for where is f prime equal to 0? Here and here. Okay, when f prime is 0, that's when the original function is going to have maximums and minimums, right? So here's a place where the slopes go from being negative to positive. The slopes go from being negative to positive. So this must be a minimum of the original function f. And likewise, here's a place where the slopes go from positive to negative. So this must be a maximum. All right, so let's see. That means at 1, I have some kind of minimum. Where is it up and down? Don't know. This could be anywhere up and down. We don't know, like if it had some kind of f of x plus some constant. If we took the derivative of that, it would still just be f prime of x because the derivative of the constant would go away. So I don't know where this is. There's no right-wrong answer about that. So I'm going to, since it's a minimum, I'm going to try to make it like kind of low here. I'm just going to sketch a little bit of a curve there to indicate to myself that I need to have a minimum there. And then here at about 1, 2, 3, 4, 5, here I have some kind of maximum. So somewhere obviously higher than this, I'm going to put some kind of maximum. And then what about the rest of it? Well, the rest of it is just sketching pretty much. We might note here that this is where f is the most positive slope. So as it goes from here and eventually bends back down, then right here in the middle, that's where it has the most positive slope. So something like that. And if you're going to apply that same reasoning here, hey, this looks like it's x squared, and the derivative of this would be x to the first, then if we went back a step, well, I mean, that hard to figure out what the power rule backwards would do. It would have to be some kind of x cubed, and that looks like a cubic function just fine. All right, so if that's all like, okay, I think that's kind of making sense, you could take just a minute to pause the video and try this one on your own. And I'm going to go ahead and charge in and do it myself. So I'm going to do things in the same order that I did for number 1. I'm going to make a graph of f double prime first. If this is f prime, then f double prime, that's just the slopes of this. The slope here, it looks like it's pretty dang close to 0. I'm assuming that this is a little pixelated like from a calculator screen, but I'm assuming that this is like an asymptote, that this is still like kind of creeping up. It's just like, that's the best that the calculator could do there. So some slopes that are close to 0 but just like barely positive, and then it's getting more positive, and here it looks like that's where it's the steepest. So somewhere around here the slopes are as steep as they ever get, and it's not that steep, it looks like it's only about 1 or something, and then they decrease and get back to almost flat. Looks like it never goes down, it never has any negative slopes. So maybe something like this is what f double prime looks like. Now in this one here, the first thing that I looked for was maximum or minimum, because that told me where the slope was 0. And this doesn't have any maximums or minimums. It has places where the slope is close to 0, but there's no maxes or minimums, and that corresponds to this not crossing the axis. All right? How about getting back to f? Okay, different mode of thought now. So these are the derivatives, and the first thing we look for is where is the derivative equal to 0? Right here. So that is a maximum or a minimum. Now this is a place where the slopes go from being negative to positive, right? Negative values to positive values. So negative slope to positive slope, that is a minimum. So it's going to have some kind of minimum here. Where is that? Like pretty close to here. So I'm going to, since it's a minimum, I'll draw that in here. Something like that. I'm going to connect stuff to that. And then here, the slopes look like they're fairly constant and negative, right? And then it starts to get less steep as it gets to this. So I have negative slopes coming into this, and then like curving like this, something like that. If you're like, oh, it's just a parabola. No, it is not a parabola. A parabola would not have a derivative that looks like this. A parabola would have a derivative that's a straight line. It looks like a parabola. No, you know what? I don't even want to say that. It doesn't look like a parabola. There's lots of curves out there in the world. Not every single thing that's like a bendy, uppy kind of shape. They're not all parabolas. This is something else that must look something like this, that f function. All right. How about this? Some calculator work. Hey, what's that? A calculator. So use your calculator to graph this. And so there's some directions here about the window. Make sure you're in radian mode. All right, I'm going to go ahead and follow those directions. So we want to graph this natural log x times the sine of x. And I want to make sure that I'm in radian mode. That wasn't. And I want to set the window to 0 to 10. Oops, that's not how you do that. 0 to 10 and -2 to 2. All right. That looks good, and graph that. Nice looking graph. Sketch the graph below. So here's my f of x. It looks like starts out here, down a little bit. This says sketch, so I don't want you to be stressing out too much about how perfect this is. Oh, I made it a little bigger than I wanted to. Something like that. And use your calculator to create the graph of f prime and then sketch that graph. How do you do that? I'm going to show you. So your calculator, the people who made this calculator, here's probably TA84, some version of that, people who made these things knew that we were going to use them to do calculus. And in the calculate menu, there's this dy dx for finding slopes. But there's also, in the math menu, if you scroll down, there's this thing that's called n-deriv, and yours looks even better. Yours looks even more like a derivative. And I should have borrowed, dang it, I should have borrowed a TI-84 from somebody so I could show you what that looks like on an 84. Well, I can write it on here on my page. And I don't know, maybe there's one or two of you out there who still have a TI-83, so I'll show you what the syntax looks like here. So what I'm going to do on my calculator, my old TI-83 Plus, I'm going to go to y equals, and in y2, I'm going to go to math 8, that's that n-deriv, and the syntax for me is, the first thing I put in is the function, so I could type in natural log x sine x. I could type that in again, but I already have that in as y1. So instead of typing it in again, I'm going to go to variables, and I'm going to go to y variables, hit enter because I'm in function mode right now, that's where it is, and hit 1 to bring up y1 there. So that refers back to this. I don't have to type it in again. Comma, and then I need to type an x here. That's just telling it like the d what. That's like in your fancy calculator, you're going to have something that looks like d, and then a little dotted thing here, and then line and x equals, and then a little dotted thing here, and then dotted thing here where you put in the function. So I have to enter the same three things. I hope that's what it looks like. I think that's pretty much it. So the y1 is the thing that goes here, right? That's the thing that we're taking the derivative of. The first thing here, that's the dx. That's the first one for TI-83 users. And then at x equals, well, here's the thing. I don't want it to take the derivative at some particular value like 1 or 2 or whatever. I want it to take the derivative everywhere and then graph all of them. So I'm going to put another x here. When your calculator graphs something in its little tiny calculator brain, what's happening is it's scrolling across the screen and plugging in all of those different x values. So it's letting x range from, in this case, 0 to 10 in very small increments to match up with the pixels. So here, as it scrolls through and makes that graph, I want it to set x equal to each one of those x values and find the derivative at each one of those places. You might be wondering, how does the calculator know how to do this? How does a calculator know how to do calculus? The answer is, it doesn't. And when I get to this number 5 here, I'm going to talk a little bit more about how the calculator is coming up with these derivative numbers. So I'm going to punt on that just for a minute, and then let it graph my derivative. So, I mean, I could sketch the derivative myself, right? Because I could look at, where the maximum, there's a minimum here, so that's a place where the derivative is 0. There's a maximum here. I could do that, but here I've got the calculator to sketch it for me. So that's coming up from here. This is the one that starts out on top here. That's a good question. How would you keep these straight from each other? Something like that. I'm not looking for perfection here. Let me show you one other trick in case you don't know this. You could go over to this all the way over to here, and you can choose the kind of line that it makes. So if you're graphing two things, like a function and its derivative, and you get a little confused about which is which, you can change that. I just hit enter one time and it changed it to a bold line. Depending on your calculator, you might even have like a color option. How is it graphing them both at the same time for me? That's because I'm in that simultaneous mode. So this is pretty cool. You can see the relationship between these. Like when that gets to a minimum, that's when this crosses. That's the steepest that ever is. And there's a maximum, so it crossed again. That's kind of a nice little show to watch there. All right. What else does your math teacher want you to do here? Find the equation of the tangent line to f of x at x equals 2. Okay, to do that, I'm going to need a point. Why did I write an x there? I know what the x is. It's 2. I need a point, and I need slope, f prime of 2. Well, I've got that all right here, right? I just need to find stuff. So here, at x equals 2, there's my y value. Now, if there's any doubt about which function it's doing, right here it tells me this is, it tells me that it's plugging into the y1 function. If you're like, oh, dang it, I want the other one, you can just bump down. I just hit the down arrow, and it moves to the other function. So those are actually the two things that I need, right? I need the point 2, 0.630, and f prime of 2 is, well, this is f prime right here, my end deriv, and that's 0.166. Why, Mr. McGrath, you might be wondering, are you rounding to 3 decimal places like this? Because the College Board told me to. So this is the first time we're doing this kind of calculator work, and it's the first time I'm telling you that this is what the College Board wants. They want us to round to 3 decimal places. So we will do so because we are subservient to the College Board. Whatever they want us to do, we do it. All right. What's 3D? Find the equation of the tangent line, another one at x equals 7. So just another chance to practice that. So why don't you go ahead and pause the video and see if you can do it at x equals 7. Pause. You try. Got to make these moves yourself. All right, welcome back. Let's see if we can crank these out real quick. So I'm going to go to second calculate, value, and x equals 7. Here's my y1. That's my function value. So 1.278. So that's always to 3 decimal places. It's not sig figs. It's how many decimal places, always to that third place. And f prime of 7, bump down there, is 1.561. Right? There's in the video for the second sheet that you're going to check answers with, I might have done that in a different way so you can see some other functions, other ways that you can do that with your calculator, perhaps. So y minus 1.278 is equal to 1.561 times x minus 7. There's your tangent line. All right. If you wanted to, you could just go ahead and, just for fun, you could put in these tangent lines so you can see them being tangent to your function, moving that to the other side, plus 0.166 times x minus 2, and y equals 1.278 plus 1.561 times x minus 7. There's that tangent line right there at 2. And here's that tangent line at 7, which is over, where's that, up here somewhere. Right? Cool. You get a t-shirt with that on it. How awesome would that be? Nerd. All right. Answer the following questions based on the following graph of f prime of x. This is a lot like these things that we just did here, but I think this is easier because we just have to answer a couple questions. This is f prime. Where is f of x increasing or decreasing? Well, f of x is increasing. That means that f prime, the slopes would have to be positive. So where is this positive? Not where's the slope of this positive, where is this positive? Because these are the slopes. So it looks like below -2. So remember this interval notation? And so it's from -infinity up to -2. It's positive in here, right? It's above the axis. Those are all positive slopes. So that's 0 to 2. And that's it. Now, you might be wondering, oh, could I include the endpoints in those? You can go either way. It's kind of a technicality, and once you get into sort of another level of proving things in calculus, which we're not really interested in, I'm usually going to write those as open intervals, and both the College Board and myself, we don't care about the inclusion or not of those. So don't worry about it. Where does f of x have maximums and minimums? Well, it has maximums and minimums where the derivative is 0. So here's a place where the derivative is 0, right? Where the derivative is 0, that's where you get a maximum or a minimum, right? So here the slopes are going from positive to negative, from positive to negative. So that is a max at x equals -2. And then here, the slopes are going from negative to positive, from negative to positive. That's a minimum. Minimum at x equals 0, and it looks like another max at x equals 2. All right. So here, here's some information. I pulled this off of some county website. This is real data. This is the actual numbers. Didn't make it up. What's the meaning of the slope of this function? Would it be a function? Would it pass the vertical line test? Think about that for a second. If you're still thinking about it, pause now so you can continue thinking about it. Come back when you're done thinking about it. The answer is yes, this is most definitely a function. It has to be, because you can't have a population at any given time. We take these as like snapshots in time. You can't have two different populations that go at the same time. You could argue that like over the year 2000 it changes, but that's not the point. This is like on January 1st of 2000 or whatever. So it can't be more than one thing. It's fair to call this a function. What's the meaning of the slope? Well, let's see. The slope would be rise over run, or the change in this over the change in this. So it would be the rate of population growth, or possibly decline or decay. Decay is a morbid way of talking about that, I guess. Rate of population growth or decline in Rockbridge County. In the units would be people, that's the units of this, per year. People per year. Find the average slope from 2000 to 2008. What does this number mean? So let's see. That would be rise 2,200,363 minus 20,835 over run 22,363 minus 20,835 over 8. Let's see how I did that in my head there. 191 and the units of slope are people per year. So what would you call this? What does it mean? This is the average increase in population each year. Average, right? This doesn't mean that in any particular year that it did this. That's the average. Create a table of slopes, and if you're in AP Physics, then we've done this before with to create velocity data, and because you have a little bit of an advantage there. These are just years past 2000. Oh, I made too many. How did I do that? 0, 1, 2, 3, 4, 5, 6, 7. Thought I divvied that up the right way. Apparently not. Okay, so there we go. So how are you going to find the slope, for example, of 2001? Well, to find the slope here, you're going to say, for most curves, most of the time, it's a pretty good approximation to say the slope here is approximately equal to the slope that connects the 2 points on either side of it. Right? So if you had like something curving like this, what's the slope here? If you took a point here and a point here, that is going to be about the same slope, usually. It's not always perfect, but it's a good estimate. So that's how we're going to do it. So to find the slope at 2001, I'm going to use the points on either side. I'm not going to use the 2001. So that's going to be this 20,989 minus 20,835 all over 2. That's 77. And then you can fill in the rest of those. And how do you do the endpoints? Because I don't have another point on this side. So when you're stuck at an endpoint, then there's nothing really better that you can do than just use that endpoint and the one next to it. So it's not a great compromise, but we don't have another point, so it's better in this case if you want a complete table, better than leaving it blank. In physics, we didn't need that complete velocity data, so we just left that out, and that was fine. So here we got 20,905 minus 20,835. But I could have done that in my head. 70. I knew it. And I'm just dividing by 1 because there's only 1 year there, so that's about 70. And you can go through, I'll let you do the rest of that, and find where the slope is the greatest. What does it mean? That would be the year with the largest increase in population. Right, that's when it's increasing the most. That is how you do that. I'm going to leave the video running for 1 sec. I'm just going to see if I have an answer key for this so I can, I don't want to make the video longer and actually bore you with the calculations, but I'm going to see if I can grab that so you can see those numbers. Coming right back. I think I have it somewhere around, let's see. Can you still hear me? I'm on the other side of my room. And, oh, I think I found it. Here it is. Here I come. I'm coming back. Coming back. Oh. That's too funny. Look at what it looks like on my answer key. I didn't do it there either. I didn't make the table. What a lazy person. I did make it for the next one. All right, so in sheet number 2, if you have any questions about that, I think it's pretty straightforward. So sorry about that. See you next time.